All right. In this video, I want to start talking about section 4.4, which is about span and linear independence. And I want to start with a kind of baby version of what we're going to talk about. So this video will just be about span. Linear independence will come later. But I want to talk about what is the set A times a vector where A is going to be a real number. Just for concreteness, let's say, let's let U be the vector, say 1, 2. Okay, just to pick a vector, just to be perfectly concrete about this. So I want to think about what is the set of multiples of this vector going to look like. And if you want, one of the things that you can do is we can draw our axis and we can think about, we have the vector 1, 2. So that's going to take the origin to this point 1, 2. And so that vector is going to map the origin to that point 1, 2. And let's think about what other vectors we're going to be able to get by looking at the multiples here. If we were to double this vector, what would happen is we would get a vector that's essentially twice as long. Let's make the double of it purple. So we would get it twice as long in the same direction, so along the same line pointing in the same direction. If we were to make the value, say, -1/2, what we would get would be a vector that's half as long as the original vector, along that same line, but pointing in the opposite direction as the original vector u. So again, let me just write out what we did here. So k times u, k being 2, I should just put in, was the vector 2, 4. And -1/2 times our vector was the vector -1/2, -1. Okay, and so what I want to do is I want to think about what happens if I let this vector scale as much as I want. So I'm going to let it stretch kind of in the positive direction to infinity and in the negative direction to infinity. And to help us figure out what's going to happen, I have a graph here that I'm going to share. Okay, so I'm going to share this graph here. And what I want to do is I want to think about what's going to happen if we take our vector, say 1, 2, and then we let it scale. And if you think about all the points that this is going to end up with, now I have a point at the end of the vector, and remember that the reason for that is that I want to be clear that vectors and points aren't exactly the same thing. Vectors are objects that have a magnitude and a direction. Points are just zero-dimensional, they're just points. And so they're not the same thing at all, but you can put them kind of in a one-to-one correspondence in the sense that you can always start the vector at the origin, and then whatever point that vector ends up on, you can identify with the whatever point you started with. So in our case, we can think of the point 1, 2 just as a point with no vector at all. Okay, and that's a perfectly reasonable thing to do. Or we can think about it as kind of the tip of the vector 1, 2, where we're talking about the vector 1, 2. So anyways, what I want to do is I want to scale this vector, and then I want to think about what's that tip of the vector going to do as it moves along. And so let's let this run. And it turns out that if the vector gets scaled, it's going to look something like this. Okay, so now we're going to get smaller and then negative. And if you think about all these points, we can actually turn on, we can let this trace itself out. But if you think about all the points that this is getting, it's along the line. So this is kind of going to pick up a bunch of points along the line. In this case, since the vector that we started with was the vector 1, 2, we're picking up all the points along the line y equals 2x. Okay, it looks like there's gaps in the line. There's not really. It's just that the step for how we're scaling the vector is like every hundredths of a unit. So occasionally, just graphically, it looks a little bit funny. But anyways, we should theoretically, if we scale at small enough scales, we should really get a completely filled in line here. And that line that we're going to get is the line y equals 2x. Okay, in fact, I've drawn the line. You can't even see it because it's underneath all those points. Okay, so here's y equals 2x. Let's get rid of those points. And if we get rid of the points, there we go. So there's the line y equals 2x. Okay, now what I really want to do is I want to play this game with, a pair of vectors. Okay, so I want to play this game with a pair of vectors. And I want to think about, let's start with the vectors 1, 2, and say 3, 1. And I want to think about what is the set of scaled and added sets of vectors u and v. Remember that this is really, what I want to say is what's the set of linear combinations of the vectors u and v. So a linear combination is a set exactly of this form, au plus bv, where a and b are constants. And I want to think about what are the vectors that I can write as a sum of these two vectors, possibly scaled vectors. So for example, I know that this set includes things like the vector 1, 2, because I could let b be 0, and if b is 0, so that piece would be gone, then a is 1, and we would just get the vector 1, 2. Likewise, we could let this include the vector 3, 1. We could add these together to give us the vector 4, 3. We could take 2 times the first vector plus the second, and that would give us 5, 5. Okay, so this is all the things that we could write as a linear combination. And in fact, you can do more than that. You can say scale the first one by pi and the second one by 2. And you would end up with something like pi plus 6, comma 2 pi plus 2. Right, if you were to think of this as pi times the first vector, 1, 2, plus 2 times the second vector, 3, 1. Okay, so I really want to think about, can we write every vector in R2 as a linear combination of these two vectors? That's what we want to determine. That's what we're after. Okay, so can we write every vector? Let's call the vector st. So can we write every vector st as a linear combination? So as a linear combination of u and v? What do we think? Okay, think about it. What are your thoughts? I want to get a good yes, no before I move on. So just, you need to not convince yourself that you were right either way. You need to maybe raise your left hand if you think no, raise your right hand if you think yes. And so let's think about what this is going to mean geometrically. What we're allowed to do if we have the vectors 1, 2, and 3, 1, if I have the vector 1, 2, that's going to be the vector that maps the origin to that point 1, 2. And the vector 3, 1 is going to be the vector over here. Now, let's think about, let's pick some random point, say here. I want to think about, let's actually make it so it doesn't look nice. Let's pick some point here. Say 2.5, comma 2, something like that. And I want to think about how could we write this point, or equivalently think of this vector if we start at the origin, as a linear combination of the other two. Well, one way that we could do this is notice that if you were to add up these two vectors, remember that the way that that works is that you would basically take this vector and you get to move it so that its tail that it's going to start with here starts at the tip of the previous vector. And then that new vector that you're going to get by going from the origin to the tip of that new vector, that's going to be the sum of the two vectors. That's how we add two vectors geometrically. That's what that means. And it looks like there's a way, I mean, we could figure out exactly what the numbers are, but it looks like there's a way to scale this vector so that maybe if we scale it so that it looks like this, and then scale the other one so that it looks like that, it looks like there's a way that we can get that point, that we can write this vector as a linear combination of the other two. And it turns out that we can. And there's nothing special about the point that we started with. It turns out that we can actually write every vector as a linear combination of these two vectors, and I want to explain why. So let's try and do this algebraically. Let's let s and t be some arbitrary numbers, but they're fixed. We chose them ahead of time. You can pick whatever values you want if you prefer to have actual values instead of letters there, and that's totally fine. But let's try and solve for A and B. So we want to figure out what constants do we need to multiply the vector 1, 2 by, and what constant do I need to multiply the vector 3, 1 by, so that if we look at this linear combination, we get the vector st. And it turns out, you guessed it, this is a system of 2 equations and 2 unknowns. It's exactly the thing that we've been studying all semester. And so it turns out that we're going to have, basically we have to solve the system a plus 3b equals s, just looking at the first components. So what I did is I moved the a inside, moved the b inside, and then added those up. That should give us s. And likewise, 2a plus b equals t. And now what I want to do is I want to argue somehow that we can figure out values of a and b for any choice of s and t. Doesn't matter what s and t are, we can always find these values a and b. And it turns out that there's a nice way that we can argue this, and it involves determinants. So if you remember, one of the things that we proved last time, or proved in the, by last time I mean in the last chapter, so we proved previously that if we look at the, if A is a square matrix, remember square just means n by n for some n. Okay, so if it has the same number of rows and columns, then, I don't know why I can't write an n by n, there we go, thank you. So it turns out that if A is a square matrix, then the set matrix equation AX equals B has a unique solution. So there's a unique solution if and only if the determinant of A is non-zero. So if we want to figure out whether or not this system has a unique solution, it's enough to look at the determinant of the coefficient matrix. So we can think of this as the matrix 1, 3, 2, 1 times AB, which is serving as our variables, is equal to our constants ST. Okay, and it turns out that this is a matrix. The determinant is -5, you can check. The determinant really doesn't matter except to say that it's non-zero. So the determinant's not 0, it's -5, but all that matters is that it's not 0. And therefore, no matter what S and T are, we can find values of A and B so that we can write this vector ST as a linear combination of A and B. So notice that this argument that we just produced did not actually tell us what A and B are. To do that, you have to go through and do the actual Gauss-Jordan elimination, so all the like reducing, adding multiples of one row to another and so on, right? The usual method. But that's fine. We don't need to come up with an explicit method for an explicit solution for A and B. We just want to know that there is a solution. So it turns out that every vector ST can be written as a linear combination of A and B. And so the way that we say this now, and what we're going to say is that we're going to say that the vectors 1, 2, and 3, 1 span the plane. Okay, so span is the key word. Okay, so the span of a set of vectors refers to the set of linear combinations that we can obtain from those vectors. So let's formally define that. So given vectors, this is actually a more general concept than just vectors in R2. This is given any vector space V. So given any vector space V with vectors, so let's say that if V1, V2, all the way up to Vn are vectors in V, then the span of the set of vectors, the span of the set V1, V2, all the way up to Vn is going to be exactly the set of linear combinations of these vectors. So it's going to be the set C1, V1 plus C2, V2, all the way down to Cn, Vn, where the constants C1, C2, and Cn are real numbers. Okay, so this set of linear combinations we're going to call the span. Okay, this is a very important topic that we'll do a few more examples of along the way.